Hello dear students, very good evening to all of you guys and welcome to the startup series again. So in our today's session guys, we will discuss about the stiffness of a member. No doubt wherever means whatever type of method you are utilizing to solve the problem like our MDM method or our slope deflection method in our structure as a subject. So in these method we need to use the stiffness term. So to understand what is basically stiffness, this particular session has designed. Okay. So we will discuss what is basically stiffness and how we can find out the stiffness of various condition, and we'll solve some of the questions also in this particular session. Okay. So let's start this particular session guys, and let's discuss what is basically stiffness and how we can find out. And this is a very fundamental concept of the displacement method. Okay. So let's start it guys. So let us consider a spring is there. Let us consider there is a spring, and let us suppose if we have applied a force, let us consider that force is basically F, right? Now we know that guys, we will have a spring constant also, which is known as stiffness of the spring, right? So K is nothing as that is basically spring constant. This one is spring constant, or you can consider stiffness. Now let's understand what it is exactly. Usually, you know that guys, we have one relation which we are writing usually in case of spring, that is basically F is equal to K into X. So what it indicate? K is nothing as our stiffness and X is our elongation or the change in length which is occur in the spring, and F is the applied force, right? Now guys, can I say that if you apply certain force F over here, so the initial length of the spring or initial position of spring is like this. Let us consider this distance is some x1, correct? Now after applied the force, no doubt the position of the spring will get changed and the elongation will occur, and let us consider it is displaced by some distance x2. So the difference between x2 and x1 is nothing as elongation in the spring, and that is nothing as our x value, right? Which is nothing as change in the length of spring, change in the length of spring. So what is the meaning of stiffness, sir? It is the force applied to give unit displacement is known as stiffness of the spring. That means how much force I have to apply so that I can extend the spring by 1 unit. Now this 1 unit can be in terms of meter, can be in terms of centimeter, can be in terms of any dimension of length, right? But guys, we need to understand by 1 unit I need to displace the spring, then how much force I have to apply, that is called stiffness of the spring, right? Good evening, Seth. So guys, can I write here if the value of X is equal to 1, then how much force you have applied? That is equal to K, and it is nothing as our stiffness of the spring, right? So tell me guys, if you apply the force F or if you apply the force K for 1 unit of displacement, and let us suppose if our spring is extended by X distance, then how much force we have to apply? K into X, right? Then how much force we have to apply? It is K into X, right? But guys, we know that we are dealing with the beams, our continuous beam, fixed beam, and other type of beams we have, right? So we need to deal in the structure part, not in the spring. So that's why guys, our terminology will be a little bit different as compared to the general stiffness definition. So in our structure part, we need to define the rotational stiffness terminology, which is nothing as again K value. Now what it is exactly, let's understand in detail. Let us take one simple example. Let us suppose this is our beam in which one end is hinged and other is fixed, okay? And let us consider this end is near end. How we can say that? So guys, wherever you will apply the moment, that particular support or that particular end will become near end, and with respect to that other end will become far end. So this is our near end where we will apply the moment, and this end will become our far end. This end will become our far end. Now let us suppose if I apply a moment at the near end in a clockwise direction, and let us consider M. Now what will happen? At this particular end or at this particular support A, the rotation will occur and our beam will try to deflect in this manner, right? So the rotation is theta A in this case, and the rotation at the far end, which is basically fixed. So this theta B is equal to how much? It is equal to 0. Now the question is, the moment required to generate unit rotation is known as stiffness of a member. Let me explain once again. It is the moment required to generate unit rotation at the near end is known as rotational stiffness or stiffness of this particular member. But this stiffness is defined at the near end itself. This value is basically KAB, not KBA, right? Because we have two values. One is KAB and second one is KBA. So usually whatever terminology we are writing or whatever stiffness we are writing, that stiffness is related to the near end value. Okay, so can I say that, guys, moment required to generate unit rotation at the near end is nothing as our stiffness of a member, right? So this stiffness is KAB multiplied by theta A. Now this theta A is equal to 1, then how much moment is required to generate unit rotation? That is nothing as our stiffness of this particular member at end A. Clear? We will find it out in our next slide. We will find out what is the value for this particular type of structure. Okay. Okay, guys. So let me explain one more point. If I ask you what should be the stiffness from B to A, what should be the stiffness from B to A? It will be 0. Why it is 0? Let's understand in the next slide or in our next thing. So general definition is what? It is nothing as it is the moment required to give unit rotation at the near end is known as the rotational stiffness or stiffness of a member. Okay. Let's understand, guys, the concept how we can find out the stiffness when we have far end as a fixed or far end as a hinge or far end as a free also. Okay. Let's understand one by one. So let us take the case 1 when the far end is fixed. Let's take this particular case when the far end is fixed. This support can be hinge or this support can be roller. That means our near end can be roller or our near end can be fixed or our near end can be hinge also, right? Where rotation can be possible. Where rotation can be possible. This is roller or this may be hinge also. Okay. Now let us suppose if I am applying certain moment at the near end, which is M, so our beam is trying to deflect in this way. Correct? So this value is theta A. This is A, this one is B, and this end is basically our fixed support. This one is fixed support and this one is what? Hinge. Now the question is, sir, what is the stiffness of this member when the far end is fixed? That is the question. So let us consider we have a length, we know the property of material E, and we know the cross-sectional property of member, which is basically I, which is known as moment of inertia, right? These values are known to us. If we apply the moment on free end, I will explain all the conditions and I will explain how we can find out the stiffness in various things, right? I will tell you, right? When we have far end as a free, then what will be the stiffness? If you apply the moment at the free end, if we apply the moment at the fixed end, I will tell you all of these things, right? Just hold on, Seth. Okay. So let us understand, guys, this particular condition. So how we can find out the stiffness of this particular member? So guys, if you want to find it out, you need to use the strain energy concept, right? So let us break this particular structure. Let's break this particular structure. Let us consider there is a reaction which is nothing as VA, which is applied at support A. This end is fixed. Let us consider length is L, this is E and this is I, right? So what we will do, guys, we'll try to find out how much displacement can be there due to VA reaction. If only VA reaction is present at this particular support, then what should be the value of displacement in the vertical direction? That is nothing as our delta 1 value. So how much it is? Delta 1 is equal to VA L cube by 3EI. VA L cube by 3EI. This is nothing as our delta 1 value. In the same way, guys, we need to find out what should be the displacement of support A when only moment is applied, like this. So what will happen? Our structure will deviate like this and this value is nothing as our delta 2. So what is the value of delta 2? Delta 2 is nothing as it is basically ML square by 2EI, correct? Now tell me guys, in the present condition, the net displacement of joint A is equal to how much? It is equal to 0. The net displacement of joint A is equal to how much? It is equal to 0. So can I use this particular compatibility equation? That means delta 1 plus delta 2 is equal to how much? It is equal to 0. And we'll use this concept to find out the value of VA reaction first. Okay. So let's write down delta 1 plus delta 2 should be equal to 0. So delta 1 is how much? VA L cube by 3I. And delta 2 is equal to how much? ML square by 2EI, and it should be equal to how much? It should be equal to 0. Let's calculate the value of VA. How much we are getting? VA L cube divided by 3EI is equal to minus ML square by 2EI. Guys, if you are not able to understand anything, please let me know. I will explain once again, or I will explain whatever doubt you have. Okay. And you can cancel this particular value easily. So ultimately you will get the value of VA, and it is equal to how much? Minus 3M by 2L. So this is our VA reaction in terms of M, which we are getting right now. Now the question is, sir, I need to find out the value of theta A, or I need to find out the value of stiffness of this particular member at support A. How I can do it? So guys, you need to use the concept of strain energy to find out the displacement, or to find out the rotation at support A. Okay. So let us apply the reactions over here. This is VA. This support is fixed right now. This value is VA, and VA is equal to how much? Minus 3M by 2L. And this is our moment which we have applied externally. This length is L. Now let us take a distance X from support A and try to find out what will be the bending moment equation at this particular section. Let us consider this section is XX. So what will be our bending moment equation? MXX is equal to how much? Plus VA into X plus M, correct? Now what is the value of VA? It is minus 3M by 2L multiplied by X plus M. And this is nothing as, this is our MXX value, right? This is our MXX value. Okay, and this relation can be valid from 0 to L distance in the structure. So we can apply this particular relation from 0 to L easily, correct? Now guys, we'll use the concept of strain energy, and at the same time we will apply the concept of Castigliano's second theorem, by which we are able to get the value of theta A. And you know that guys, as per Castigliano's second theorem, if you calculate the total strain energy of a structure, and if you take the first partial derivative of that particular strain energy with respect to any force, so you will get the displacement which is produced by that force in that direction, right? Or in the force direction. So let's do that, do this particular thing, guys. So total strain energy is equal to integration 0 to L mxx square dx divided by 2EI. Okay, let's put the value. So total strain energy is equal to integration 0 to L. What is the value of mxx? It is minus 3m by 2L into x plus m bracket whole square dx upon 2EI. This is our equation, yes or no? This is our equation. Now what we will do, guys, we'll take the derivative of this particular total strain energy as per Castigliano's second theorem. I will explain it, guys. Those students who are new over here, or those students who don't know about the Castigliano's second theorem, let me explain in a very short. Okay, so as per Castigliano's second theorem, we can write down, let us suppose this is our member in which we have applied certain force. Let us consider F. And in the direction of force, let us consider some displacement is occurring, which is nothing as delta. So as per Castigliano's second theorem, we can find out the total strain energy of the structure. Then you have to take the first partial derivative of the total strain energy with respect to the force in which direction you have to find out the displacement, right? So let us consider, if we take the derivative of this particular total strain energy with respect to F, so we'll get the displacement in the direction of force itself. That is basically our delta value. Clear? Okay. Now guys, let's do the same thing in case of this particular condition. Now tell me what you have to find actually. We need to find out the value of theta A. How we can find it out? First, we need to take the derivative of the total strain energy with respect to m so that we can get the value of theta A, right? Let's do it. So del ut by del m will give us theta A value, and it should be equal to integration twice minus 3m by 2l into x plus m. Then again we have to take the derivative of it. So how much it is? It will be minus 3x divided by 2l plus 1, then dx divided by 2ei. You can cancel 2 to 2 easily, right? And this value is equal to how much? It is equal to theta A, and the limit is 0 to L. Now whatever constant value you have, please take out as a common. So m by ei is the constant value which we can write down outside the integration part, and then we have to write integration 0 to L, and this value will become minus 3x by 2l plus 1 whole square dx, correct? Okay, so theta A is equal to how much? It will be equal to m by ei, then integration 0 to L. Now let's expand the equation. So this value will be 9x square plus 4l square minus 12lx minus 2ab, that means, and this value will be 4l square, correct, and dx. So theta A is equal to m by 4l square ei, 4l square ei. And now do the integration part, then we'll put the limit. So this is 0 to L. So if you integrate it, what you will get exactly? 9x cube divided by 3 plus 4l square into x minus 12lx square divided by 2, correct? Now cancel this, you will get 6. Okay, you can cancel this also, it will be 3. Okay, now let's put the limit to get the value of theta A quickly. So theta A is equal to how much? Tell me guys. Theta A is equal to m by 4l square ei, and this value is how much? 0 to L. So guys, this is 3l cube plus 3l cube plus 4l cube minus 6l cube, right? And if you put the 0, it will be 0, right? So we don't have to put the lower limit, it is not required. So guys, if you solve this, you will get L cube at the top. That means ml L cube divided by 4L square divided by EI. You can cancel this value, so you will get the value of theta A. So what is the value of theta A? Theta A is equal to ml upon 4 EI. Now tell me guys, what is our definition of stiffness? It is the moment required at the near end so that we can get the unit rotation at the near end. That is known as stiffness or rotational stiffness of a member, correct? So guys, what I will do, I will put theta A is equal to 1, then how much moment I required at the near end so that that particular support can rotate by, that particular joint can be rotated by theta is equal to 1. So m is equal to 4 ei by L multiplied by theta A, and theta A is equal to how much? 1. If it is 1, then our stiffness from A to B is equal to how much? It is 4 ei by L. And usually you have seen when the far end is fixed, the stiffness of a member is how much? It is 4 ei by L. It is 4 ei by L. I think it is crystal clear to all of you. Yes or no? Tell me guys. Crystal clear? How to find out the stiffness of a member? Vinay, Saif, please write down. Very nice. Now, there are some students who are asking, sir, if we are finding this stiffness when the far end is fixed or near end is fixed or near end is free, so how we can do it? So let's understand the concept when the near end is fixed, okay? So what will happen? Let me explain. Let us suppose this is hinge and this one is our fixed. Now what we are trying to do, we are trying to apply the moment at the near end again and this end is fixed basically, okay, and this is B and this is A. Now tell me guys, if you apply the moment at end B, then what should be the rotation at end B by this particular moment? Tell me guys in the chat box quickly. What should be the value of theta B? What should be the value of theta B? It is possible to rotate this joint? No. Why? Because this is a fixed one or this is a rigid joint, right? We are not able to rotate it. So that's why theta B is equal to how much? It is equal to 0. If theta B is equal to 0, can I write here m is equal to kBA multiplied by theta B. But theta B is 0. If theta B is 0, then tell me what is the stiffness from B to A? From B to A, it should be infinity. It should be infinity. It is not equal to 0. It is basically infinity value. Now tell me guys, in case of a beam where far end is fixed and near end is hinge or roller, what we are trying to do? We are trying to find out the stiffness, and usually the stiffness is defined at the near end, which is basically hinge or roller. The value is 4 EI by L when the far end is fixed. Crystal clear? So the first one is very clear to all of you, I think so, and you are able to understand how to find out the stiffness in such condition. Clear? Okay, very nice. Let's understand the next concept guys. When the far end is roller or hinge, let us take another concept. Let us take this particular support is hinge and this one is roller. Now let us consider this end is near end and this one is far end, and we are trying to apply the moment at the near end. Let us consider M, due to which rotation will occur. This rotation is theta A and this rotation is theta B. And let us consider the support is A, the support is B. And L is length, E is Young's modulus of elasticity, and I is moment of inertia. Now guys, let us consider the reaction at support A is VA. So can I find out what is the value of VA easily? Yes, we can write here guys, summation moment at B is equal to 0. That means VA into L plus M is equal to 0. So the value of VA is equal to how much? It should be minus M by L. This is the value of VA which we are getting. Okay. Now tell me guys, after knowing the reaction VA, it is very easy to write down the moment equation at any distance x on the structure. Correct? Let us consider this is VA and this one is M which we are applying. And let us suppose the distance which we are taking is x. This distance is x. Now what we will do guys, we will try to find out the equation of moment at section xx. So mxx is equal to how much? It is equal to VA into x plus M. Correct? Now what is the value of VA? It is minus M by L multiplied by x plus M. Now guys, we will find out the total strain energy again. So total strain energy can be written as 0 to L minus M into x divided by L plus M bracket whole square dx divided by 2EI divided by 2EI. Now again the same thing we will apply guys, Castigliano's second theorem. We'll take the derivative or first partial derivative of the total strain energy with respect to M so that we can find out the value of theta A. So del ut by del M is equal to how much? Del ut by del M is equal to how much? Integration 0 to L. So twice minus M into x divided by L plus M. Then again take the derivative of it, minus x by L plus 1, and then dx divided by 2EI. Kindly cancel 2 to 2. Okay. And this value is equal to how much? It is equal to theta A. So theta A is equal to integration M by EI bracket minus x by L plus 1 whole square and dx. Now let's do the integration once again guys so that we can find out the rotation at support A, and then we will use the concept of stiffness to find out the value of stiffness again for far end is hinge or roller. So the limit is 0 to L. So x square plus L square minus 2LX divided by L square. right? And then dx. So m by ei L square, and after integration the limit is again same, m 0 to L, and this value will become x cube by 3. This value is L square into x minus 2L x square divided by 2. You can cancel this value. Okay, now let's put the limit to get the answer. M by ei L square, and if you put the limit it will be L cube divided by 3 plus L cube minus L cube. Kindly solve this, you will get the answer. How much it is? Theta A is equal to how much? Theta A is equal to, this value is how much? L cube by 3, and this value is m by ei into L square. So m L cube by 3 ei into L square. Kindly cancel this. So you will get the value of theta A, and theta A is equal to how much? Theta A is equal to ml upon 3i. Now guys, as per our definition of stiffness, the moment required at the near end to generate the unit rotation at the near end is known as stiffness. So again what we'll do this particular calculation like this. M is equal to 3 ei by L into theta A. So what is the value of K, or what is the value of moment which is applied at the near end, so that we will get the unit rotation at A. So theta A is equal to how much? Theta is equal to 1. So what should be the moment we have to apply? 3 ei by L. And this is nothing as our stiffness of AB. So when far end is hinge, then the stiffness will be equal to how much? It is 3 ei by L. It is 3 ei by L. Crystal clear to all of you? Please let me know guys. It is crystal clear to all of you? Crystal clear to all of you? How to find out the stiffness? Very nice, very nice. Now let's understand the next one. When the far end is free, then what should be the stiffness? When the far end is free, then what should be the stiffness? Now this concept is very easy in this particular case. This is A, this is B. Now tell me guys, if I apply any moment at the hinge, right? So this particular beam will try to rotate infinitely, right? So you can write here theta A can be infinity. It is infinity, right? It can rotate infinity. So ultimately we can write down M is equal to KAB multiplied by theta A. So what is the value of theta A? It is infinity. So what will be the value of stiffness? It should be equal to M by infinity. That means it is equal to 0. So when the far end is free, then the stiffness of a member is equal to how much? It is equal to 0. Now it is understood to those students who are asking this particular question. When far end is free, then what should be the stiffness, sir? It is basically 0. It is 0. Crystal clear to all of you? Please write down guys quickly. Perfect. Perfect, perfect, perfect. Now tell me the answer of these two questions first, then we'll discuss what is relative stiffness and where we can use it. Guys, there is one question, which one is the true relation between the stiffness and flexibility part? Now the question is, sir, I know the stiffness, what is stiffness, but what do you mean by flexibility? So now we know that guys, the relation which is basically F is equal to Kx, right? The force required to give unit displacement is known as stiffness, but the flexibility is inversely proportional to stiffness part. What it means actually? It is the displacement caused by unit force. That means how much displacement can be caused if you apply unit force on the structure, or you can say that if we apply unit moment, then how much amount of rotation will occur at the near end is known as flexibility, right? So that means if force is equal to 1, then how much displacement will occur? It is basically F by K, and F value is 1. So ultimately displacement is equal to what? 1 by K, and 1 by K is nothing as it is our flexibility. So the displacement caused by unit force is known as flexibility, and this is our definition. This is our definition. Let me show you that. I think it is not written. I will write it down. Okay, so flexibility is nothing as it is the displacement caused by unit force. Displacement caused by unit force. This is known as flexibility. This is known as flexibility. Now tell me guys, out of these four options, which one is the correct answer? K is proportional to F, K is proportional to 1 by F, K is greater than or equal to F, K is less than or equal to F. Tell me guys, which one is the correct relation? A, B, C, D. Can I say that it is B? B is the correct answer. K is inversely proportional to F. Correct? Let's move to the next question. The ratio of stiffness of the beam at the near end when far end is hinged to the stiffness when far end is fixed. You need to tell me guys, what should be the ratio of stiffness when the far end is hinged and far end is fixed? So you know that when far end is hinged, the stiffness will be equal to how much? 3 EI by L. And when far end is fixed, what is the stiffness of member? 4 EI by L. Now let's take the ratio of it, you will get the answer. So it should be 3 by 4. 3 by 4. Clear? 3 by 4 is the correct answer. Crystal clear? Very nice, very nice, very nice. Now guys, there is one more terminology which we have to understand, which is related to the stiffness part. Now usually what happens whenever we have a continuous beam or frames in which the Young's modulus of elasticity is usually constant. That means whatever material we are using, that material is same throughout the structure. So if such type of condition will occur, then it is very easy to cancel out it is very easy to eliminate the Young's modulus of elasticity from the stiffness part, right? So let me explain what is our relative stiffness usually. So relative stiffness can be defined as it is ratio of stiffness of a member divided by 4E, right? So this is nothing as our relative stiffness. Now let's understand in the concept part, right? So tell me guys, when you have far end is fixed, what is your stiffness? It is basically 4 EI by L. So if I want to write down the relative stiffness for the same member at the same support condition, then relative stiffness will be equal to how much? It will be KAB by 4E. So relative stiffness is equal to KAB by 4E. Now tell me guys, if you write it down, 4 EI by L divided by 4E, it will get cancelled and ultimately you will get the answer like I by L. So when far end is fixed, then relative stiffness is I by L only, and this particular term will not depend upon the Young's modulus of elasticity, right? In the same way, when we have far end is hinged, then what will be our relative stiffness? Relative stiffness is equal to how much? 3 EI by L divided by 4E. So kindly cancel this, you will get 3I by 4L. Clear? Let us suppose if far end is free, then what should be our stiffness? So relative stiffness is equal to K by again 4E. So K is equal to how much? K is 0 divided by 4E. So this value will become 0. Clear? So now I think you are able to understand how to find out the stiffness of a member by using strain energy, by using the concept of Castic nanosecond theorem, right? If you are able to understand, please write down guys yes or no. Or any doubt if you have, please write down guys quickly. Any doubt, any doubt, any doubt. Clear? Okay guys, so let me tell you something more over here guys. We are running some question series or question practice session in our app class, which you can join on daily basis at 10 AM. I am sharing that particular link in my Telegram. You can join it that also guys, and you will get the access of the app from our in the description box, right? So you can access the app classes, free app classes, which is also useful for you guys so that you can practice more number of questions. Okay. So tomorrow again we will meet guys at the same time, in which we will discuss the further concept of our structure part. Okay. So thank you so much for joining the session. Let's meet in the next one. Bye bye guys and take care.